Hi everybody, back to YouTube Gugarity again. Today is the 3rd of May 2019. What I'm going to do today is going to talk about the full adder digital circuit, and just to review for students who are going to have final exams coming in 2 weeks. So basically, what I'm going to mention is start from the basic understanding of adder digital circuit. In this case, I'm going to do 1 bit 2 of 1 bit adder. What I'm going to talk here is just about basic understanding, and then talk about how to create the truth table, and then apply Kanaugh Map to minimize terms. The output term that depend on inputs. And then I also do the circuit, and also do simulation to get the plots for more understanding. Okay, let's start with the adder circuit. In this case, I'm going to talk about the base 2 number, which in this case you have the logic status to be 0 and 1, or in the term of 0 is low and 1 is high, and then the combination, the total combination of logic state is there to be 2 to the power of second, or 2 to the second. That's in this case is 4, because we have 2 numbers of 1 bit. And then let's take a look at the logic status for input A and B, the possibility or the total combinations. When you have our input A and B, the input A and B can be either 0 or 1, as well as the B, right? So you have total 4 combinations. You have A to be 0 0 1 1, B to be 0 1 0 1. And then when you add number together, you're going to have output, sum, output, and carry. So let's take a look at when you add 0 and 0, you end up with 0 as the sum, and the carry is to be 0. And in the case of you add 1 and 1, you go to end up with sum to be 0 and carry is 1. Okay, that's we will focus on the output, sum, and the carry. And if you write down the truth table, in this case it's just for the half adder for the simplicity. So your input is the A and B, and your output is going to be sum and carry. Next, we're going to draw the digital circuit by using basic logic gate. In this case, going to be OR gate and AND gate. You take a look at the output sum. When you have input to be A and input to be B, and your sum is going to correspond to input A and B. as the actually it's the same, from the truth table here. Now for the digital circuit, if you take a look quick, and if you still remember, you take a look at the logic status of the sum to be 1. You can see that your input is the 0 1 and 1 0, and this simply is the exclusive OR gate, right? Because you know that if you have two inputs and the logic status of your inputs are different, that's give your output logic state to be 1, and also this is 1 0, and input A and B are different. So simply you can see that to draw the circuit for the output sum, simply using a exclusive OR. Next, you take a look at the output carry. For this case, for the logic status of carry, it has only 1 here, right? And this comes from the input A and B 1 1. So that means this obviously that you're going to use the AND gate, because you know the AND gate is that two input AND gate. If the input has the logic state to be 1 and 1 only, that will give you your output to be 1. Otherwise it's going to be 0. That's different from the OR gate. The OR gate is if you have input only 1, that will give you output to be 1, except your both input to be 0 and 0, that will give your output to be 0. Okay, let's move to the next step. This is the draw circuit, just to show you how to make the circuit and connect the circuit. I have input A and input B, so this is for the output sum, and this one is the output carry. And you know that for the output sum, just use expression A exclusive B, and for the output carry you just use the two input AND gate. And this one is my plot from PSpice simulation. Okay, so I'll start with the input A to be let's break this apart to be 0 0 1 1. Okay, that's for combinations. And for B, you're going to start with a 0 and then 1 and then 0 and then 1. So that's why you have input AB to be 0 0 0 1. Sorry, this is I did wrong. I should start from sorry. You have input A and B to be 0 0 and then 0 1 and then 1 0 and then 1 1. Okay, and that's your output sum, and then this is your output carry. Now let's take a look at the full adder circuit. What I just mentioned is just is the half adder circuit, because it works only half part of the process for adding numbers together. For example, if you consider the decimal or the base 10 number, two of them, you know that the decimal numbers start from 0 to 9. Okay, you don't have 10. That's what you call decimal or base 10. For example, if you add 8 and 9 together, you will get the total number to be 17. And 17 just come from 1 multiplied by 10 to the power of 1 and plus 7 multiplied by 10 to the power of 0. And 7 is come from output sum, and then 1 simply is the output of our carry. Okay, you have idea about this one. So when you add two numbers together, you have 17, and that means your 1 or carry is there in front of 7. That's how it works. So to make the adder complete, or to be the full adder, you need to have another input. In this case we call C incoming as the input as well. So instead of you have two input, you end up with 3 inputs. Let's take a look at this is your input, this is your output. You have our input C incoming, you have A input, you have B input. You expect to have our output sum and output carry. So you do the same thing, you break this one apart. You can write down, or this is for the truth table. So your logic status of C in, you can start from 0 0 0, then 1 1 1 1. So you have X, total X combinations. And now for A, you still break down to be 0 0 1 1 0 0 1 1, and for B you have 0 1 0 1 0 1. And if you add these 3 numbers together, as the input full adder circuit, you're going to end up with sum to be 0. So this is not so difficult for you to understand, and for your carry, of course, to be 0. But if you have 2 1s or 3 1s, you're going to end up with the carry to be 1 1 1, because it exceeds 2, right? Or equal to 2. Now from this point, since you have more inputs, that means your expression for output sum and carry will be more terms in the term of your input C in, input A, and input B. When you desire more complicated circuit, you need to apply a Kanaugh Map to minimize the term for your output, to reduce your number of chip or your IC, or your number of logic gates. In this case can be your AND gate or gate. And also you have less connection in your PCB board. That means your signal will show up output faster. Okay, so this is your truth table for full adder circuit, and for 3 inputs, and this is your output. Now let's take a look quick. In the case if you not apply your Kanaugh Map, you have to write down the expression for our outputs. Let's start with the output sum. Okay, and what you have is just take a look only the logic status of your sum to be 1. So in this case you have 4 of them. If you take a look at your input you have to write your output sum in the term of input C in, input A, and input B. Let's break apart. I'm going to break the sum to be I'll call this as sum 1. This is sum 2, sum 3, sum 4 for easier to understand. You take a look at the output status of sum to be 1. That's from Cn to be 0 and input A to be 0 and B to be 1. You can write the sum 1 in the term of Cin, A, and B to be what? Cin bar. In this case, bar is mean your logic status is 0, and simply B, not B bar, is simply the logic status to be 1. Okay, so in this case you're going to have C in bar and with the A bar and end with B. That's the you need 3 input AND gate. Okay, and you can do the same thing for sum 2, sum 3, and sum 4. And to get the final sum output, you need to OR this sum together, or you need to apply your OR gate, or you use the symbol as the plus sign. This one you use the dot sign for the AND gate. So you have 4 terms, right? 1, 2, 3, 4. That's why I have sum 1 to be this term. This is your sum 2, this is sum 3, and sum 4. And your sum is simply equal to sum 1 plus sum 2 plus sum 3 and plus sum 4, or in the term of your 3 inputs. And as I mentioned, the dot sign is mean you and your input together, and the positive sign is mean you or your input together. So basically, if you take a look at these expressions quick, you're going to have 4 3 input AND gate, right? And how many OR gate that you need? You need 1, you need 2, and you need 3. As mean you OR gate of your this third term together. And if you show you in the piece-price program, in the circuit that I draw it for you. But we're not going to do this one because we want to minimize, if possible, to minimize this term instead of to be 4 terms. Sometimes you can have less term, so let's do that together. And this one is the same as for carry output. Okay, I'm not going to repeat that again. You do the same thing. And to create the Kanaugh map, just take a look at this quick. This is your input Cin. Okay, you have Cin to be your 0 and 1, and this is your A input, and this is your B input. So you have it that's the in the truth table. You have 0 0 1 1 for input A, and you have 0 1 1 0 for input B. and for this part is your output sum. Okay, and for 3 inputs, you're going to have the total combination, as I mentioned before, equal to 2 or to the third, that's equal to 8. That's why you have 8 combination just right here. And to be easy, I suggest you just to put down the logic state as 1. You don't have to consider 8 combinations, and the rest you can just put 0, 0, 0 in there. Okay, so you go back to your truth table of full adder circuit. You can take a look at the output sum. So you have this one as the logic state as 1, 1, 1, 4 of them. So you break this one apart to be easier to consider. You have C in 0, 0, 0, so you do not need to worry about that. What you need to worry is just A and B. So 0 and 1 make 1, 1 and 0 make 1. So you have 0, 1, 1, 0. Let's get back to our Kanaugh map. Okay, this is your C input is 0, right? And you simply put the output logic of sum as 1. So you have 0, 1 and 1, 0. That's why I have logic state as 1 just right here, and the rest you simply put 0, 0. And you do the same thing for C in equal to 0, and you're going to have your input to be 0, 0 to get the output of sum to be 1, and also 1, 1. You have your output of your sum to be 1. Okay, and you do the same thing for your output carry. Now the next step is that how to minimize that term, because you want to write your output in the term of your input. In this case is 3. Okay, the way to do that is just to I draw the rectangular across the output logic 1 only. For this case, you cannot combine the logic state as 1 and 1 together, because they are separate. Okay, it's not like adjacent to each other. So that's why your output sum expression has to be 4 terms: 1, 1, 1, 2, 3, 4. And the way to write your output expression, you take a look at this one. Okay, if your input doesn't change, you have to put your input in the expression. Let's take a look at this one. Okay, I start this one to be number 1 or sum 1. You look down, you look from the top to the bottom for this one. You can see that it doesn't move to anywhere, or it doesn't extend to anywhere. So this one, your sum 1, has to be in the term of C in A and B. You can start writing this one. Okay, your C in is 0, so you have to put C in bar. Okay, and you look at this row from the left to the right. Your A is 0, so you need to put A bar as well. But for B input, the logic status is 1, so you simply put B and you put the dot between them to represent that they need to use the 3 input AND gate. And you do the same thing for sum 2, sum 3, sum 4, and you add them together. You use the plus sign, but it's actually you need to use the OR gate. That's what this means. Okay, so finally I'm going to have a 4th term as I put sum 1, this is sum 2, this is sum 3, and I have 4 term raised, so I need also sum 4, and you OR them together, 4 terms, OR them together, you're going to end up with your sum to be like this. And so for the output sum, you can see that you cannot minimize terms, but before I move to the output carry, let's take a look at your circuit. In this case I'm using PSpace. So basically the way you draw the circuit, just you need 3 input AND gate. How many of them? 4, right? And then how many OR gate, 2 input OR gate you need? You can also use the 3 input OR gate, but if I can also use the 2 input OR gate and then OR then later on. Okay, so you can see this expression for your output sum, and this is my circuit. I have 3 input C in, A and B, and I also have input digital logic to be 1 and this one to be 0. That's why I add inverter. Okay, so this is 1, but when you apply inverter, your output is going to be 0. That's why you need 2 logics, 1 and 0 as the input for each input. Now the circuit, as I mentioned, you need 3 input AND gate, right? And you have to arrange your input to be your 3 input AND gate, and then you need 3 2 input OR gate. So from the expression right here, finally you're going to do the real circuit. Like this. That's how you connect the circuit. So that's why I mentioned earlier, it's very important for you to minimize the number of gates used, because you don't want to make so many connections and you make your signal slow. Okay, in this case, for you can get 3 input AND gate from IC 7411, and 2 input OR gate from IC 7432, and for your inverter you can get from IC number 7404. Okay, 3 of them. And this is my plot from piecewise simulation. I have to correspond to your truth table. Okay, that means you do it right. Either you write the correct output expression here, and then you have to make a correct circuit. So the 2 steps you can actually you can be 3 steps you can make mistake. 1 is from truth table, 2 is the output expression in the term of inputs, and the last one, the way you connect your circuit. But if you're careful, it should not be a big problem. Okay. And now take a look at the output carry. We can group logic states as one because they are like close together. Okay, I will show you. So in this case we have a 3 from how many terms? 1, 2, 2 right here, 3, 4 from 3 terms. Oh, sorry, 4. 1, 2, 3, 4. We can minimize your terms by applying the Kanaugh map. Okay, let's see here. The blue one. Sorry. You take a look. Let's see. From the left to the right or in row, and for input C in, you look at C in column. So the expression for the blue one is going to be A, B. Okay, you need A and B, right? Because A and B doesn't change. But for C input, you can see that this one moved from the left to the right, and C switch from 0 to be 1. So we will not use C in. So the blue one is going to be what? A and B, right? Dot B. And for the green one, you can take a look from C input from the top to the bottom. C doesn't change. So you keep in mind that you need C, and simply C, not C bar, because logic status is 1. But for A and B, you look from the top to the bottom, you can see that B change from 1 to 0, so you don't need B. But for A, it doesn't change, it's still B1, and you simply put A, not A bar, because the logic status is what? 1, right? Now, what about the last one right here? You can do the same thing. Actually, is cover, this one. C doesn't change. You keep C. But in this case, A change, right? But B doesn't change. It still stay at 1. So you need B. From for 1, you end up with 3 terms. Okay. So it's become what? This is not clear. Okay. Let's take a look at the expression right here. So that's what you end up: AB plus BC plus AC. So in this case you will need what? 3 of 2 input AND gate, right? And then you need what? 2 over 2 input OR gate, because you have a plus sign here. So let's take a look at the circuit. You do the same thing. You have 3 inputs, right? A, B, and C incoming, and you need 3 of 2 input AND gate, and also 2 over 2 input OR gate. And this is my plot from PSpice simulation. Okay, that's all about how to design the full adder circuit. And what we need to do, we need to start by create the truth table, and then you need to do the Kanaugh map to minimize output term in the term of your input, and then finally you connect the circuit. So that's all the step you need. And keep in mind, this is the not complicated design, but when you have a bigger circuit, you have more your input and output. That will take time to finish your design. Okay, thank you very much. I'll see you later.